Dear student, warm welcome to NPTEL Phase 2 program video course on Geosynthetic engineering in theory and practice. My name is Professor J. N. Mandal, Department of Civil Engineering, Indian Institute of Technology, Bombay, Mumbai, India. This lecture number is 44 and module 9, Geosynthetics for ground improvement. Now, I will address the recap of the previous lecture, that is introduction, ground improvement technique, consolidation technique, properties of marine clay and natural prefabricated vertical drain NPVDS, and filtration characteristics of jute and polymer geotextile filter. Now, filtration characteristics of the jute and polymer geotextile filter, most important requirement of geotextile filter is the ability to retain the soil, adequate permeability and ability to resist self clogging. These are the very important parameter for the filtration and drainage for any kind of the material. Here we have shown that 4 natural prefabricated vertical drain, either woven jute geotextile or non-woven geotextile and the polymer geotextile material. These are the various type of the geotextile filter. Now, apparent opening size of the geotextile. This is very important that one should know what will be the apparent opening size or the equivalent opening size of the geosynthetic material. Now, this apparent opening size geotextile material AOS or O95 of geotextile has been performed by dry sieving method. So, here is the filter type. This is all jute material 550 and AOS or filter opening size, which is designated as O95 or equivalent opening size. This is 0.8 millimeter and this is 0.6 millimeter O50. Similarly, for the WJT 700, that O95 0.25 millimeter and O50 is 0.18 millimeter. Then WJT 775, that O95 0.16 and O50 is 0.11. And then in WJT 680, these are all gram. So, O95 is 0.14 millimeter and O50 less than 0.075 millimeter. Whereas, for non-woven polymer, this O95 is less than 0.075 millimeter and O50 also 0.075 millimeter. So, this apparent opening size of the different geotextile material is important, because here we have to observe how the water can pass through the geotextile material. What should be the required equivalent opening size or apparent opening size? This also depend upon that what will be the uniformity coefficient of the soil. So, we have already studied it, that how to design the filtration and the drainage. Here for the natural and the prefabricated vertical drain, the one of the important parameter is the apparent opening size of the geotextile that has been shown. Now, apart from the apparent opening size of the geotextile, we should also study that what will be the permeability of the geotextile filter. That is also very important factor for in the case of the drainage and the filtration. Now, permeability of geotextile filter, this is test property or unit this is geotextile filter. This permeability value for WJT 775 is 1.7 into 10 to the power minus 4 meter per second. WJT 700 geotextile filter is 2.0 into 10 to the power minus 4 meter per second, and WJT 550 is 3 into 10 to the power minus 4 meter per second. In WJT 680 is permeability value is 6.5 into 10 to the power minus 4 meter per second, whereas non-woven polymer geotextile, that permeability value is 1.1 into 10 to the power minus 3. So, this is widely recommended criteria that is given by Rixner et al. 1984, Bargado et al. 1996a, Royce 1997, Bow et al. 2000c, that permeability of the geotextile filter used in the prefabricated vertical drain should be greater than 10 times the permittivity of the soil. So, if it satisfies this criteria, so you can make use of this natural prefabricated vertical drain. So, these two criteria should fulfill. What is the apparent opening size of the prefabricated vertical drain as well as the permeability of the prefabricated vertical drain. Then some compatibility of jute geotextile filter with marine clay, because the jute geotextile are to come in contact with the marine clay when you install this prefabricated vertical drain. So, what is required? That long term filtration test. It requires hydraulic conductivity ratio test, that is called the HCR test. So, for the long term filtration test, and this is the schematic diagram, is fabricated for filtration test apparatus in IIT Bombay by Dr. Asha, and this is the filtration test is in the progress. So, this I have already discussed in detail the earlier chapter where I talk about the filtration, drainage and erosion control system chapter. So, here is the geotextile material and this is the marine clay, like this. Here filtration test is in the progress and you can measure that what will be the water level, and then you can find out that what should be the filtration characteristics of the material. So, from this test you can correlate the relation between the system hydraulic conductivity, that is meter per second, to time in days. So, these are the marine clay polymer filter whose apparent opening size is less than 0.75 millimeter, and also the marine clay with the natural woven jute textile 680 filter whose apparent opening size of filter is 0.14 millimeter system. So, with these two systems you can see that it is almost the matching, and also the hydraulic conductivity, you can see that they are increasing, it reached to this top and then it is coming down and almost this constant. After 30 days, 40, 60, it is remain the constant. So, with time passes, how you can see that hydraulic conductivity behaves. And these two, the material, one is the polymer material, another is the natural prefabricated vertical drain, and both also almost giving the same result. Therefore, we can conclude that the natural prefabricated vertical drain also can be used and it satisfies the long term behavior of the marine clay in geotextile filter system. There is another curve for the relationship between the systematic hydraulic conductivity versus the time in days. Here marine clay and open jute geotextile 775 filter whose apparent opening size is 0.16 millimeter system, marine clay WJT 700 filter and apparent opening size of geotextile is 0.25 millimeter system, and marine clay open jute textile 550 filter and apparent opening size 0.8 millimeter system. You can see that all these system, you can see that nature of the curve, okay, with increasing, this is the time versus the hydraulic conductivity, increasing, then it is after maybe the 10 or 15 days, and then it is decreasing after 30, 40 days, 50, 60, and then almost remain constant. That means it will be in a state of equilibrium position and it is in a state of stable. So, within a short period of the time. Now, apart from this, we have performed the hydraulic conductivity ratio test, HCR test. So, this also we have described in the filtration, drainage and erosion control chapter, and this is the hydraulic conductivity test ratio, the setup, and here is a triaxial the chamber, this is pore water pressure transducer, this is flexible wall permeance cell, and here is the volume changes indicator, here is the data logger, and this is backup pressure system, and this is cell pressure system. So, when you perform this hydraulic conductivity ratio test, there are 3 stages of HCR test. First, saturation of marine clay geotextile filter system. Second, primary consolidation of marine clay. And third, that initialization of flow. So, this also have been described. Here I am just showing some result of the HCR test. This is the hydraulic conductivity ratio versus the pore volume. So, this is the variation of hydraulic conductivity ratio with the pore volume. So, this is marine clay, the red, this is marine clay polymer filter system, and this is marine clay open jute geotextile 775 filter system. You can see here that how the hydraulic conductivity ratio is also decreasing with increasing the pore volume, and then after 2 or like that it is almost this constant. And this is also similar nature of the curve for both the polymer filter system as well as natural open jute geotextile 775 filter system. So, it also satisfies this criteria that what should be the pore volume or the hydraulic conductivity of the ratio of the pore volume. So, next also this is the variation of hydraulic conductivity of marine clay geotextile filter system with time. So, here also the same, the marine clay polymer filter system and the marine clay then open jute geotextile 775 filter system has been shown. You can see here that how the hydraulic conductivity here it is decreasing, and with increasing the time in days, and then almost after 15 days it remain also the constant. So, these also satisfy this criteria for both cases, for polymer filter system as well as the natural prefabricated vertical drain system, while in both cases marine clay also have been used. So, soil retention criteria relationship, this is very important, soil retention criteria. So, from the present study we have the criteria that O95 by D85 and O50 by D50. So, this is the filter type, this is the all natural 4 geotextile prefabricated vertical drain, and this is the non-woven polymer drain. You can see that ratio O95 by D85 for natural, this case is 2.7, for WJT 700 is 4.2, WJT 550 is 13, in WJT that is 680 is 2.3, for non-woven polymer it is less than 1.25. And O50 by D50 for WJT 775 is 58, WJT 700 is 94.7, and WJT 550 is 315, and in WJT 680 is less than 39.5, and non-woven polymer is less than 39.5. So, here that Christopher and Holt's 1984 for polymer filter material, they found for woven it should be less than equal to 1, for non-woven is less than equal to 1.8, and O95 is less than equal to 0.3 millimeter. But vertical to ETL 1996 for that prefabricated vertical drain, this value is less than equal to 3, and also this is less than equal to 18 to 24. Bow ETL 2000C for the polyester prefabricated vertical drain, and this value is lies 4 to 6. So, here that D85 of marine clay is 0.06 millimeter and D50 for marine clay is 0.0019 millimeter. But what are the criteria, retention criteria for this present study? So, retention criteria for the present study, that O95 by D85 should be less than equal to 4.5. So, you can see that some cases here also this ratio is less than equal to 4.5. This is the criteria you require. So, it satisfying the soil retention criteria. So, here because soil retention criteria also very that important. So, whenever you will design for any filtration and drainage, so you should go through the gradation curve properly, because D85, D50, these are the data or parameters are very important. Now, summary and conclusion. The apparent opening size testing of non-woven jute geotextile from dye sieving is time consuming. From the test conducted on non-woven jute geotextile, it is conducted that dye sieving may not be a suitable method to find the apparent opening size of non-woven jute geotextile. But majority of the cases we have performed the dye sieving case. The permeability of all the jute and polymer geotextile filter is 10 times more than the permeability of the marine clay, and thus satisfy the general recommended criteria used for filter used in the prefabricated vertical drain installed in clay. From the long term filtration test for the given soil and hydraulic condition, the maximum system permeability is almost same in all the 5 systems, measuring 1.4 into 10 to the power minus 8 meter per second. Multiply increase and decrease pattern in system permeability with time are observed before reaching the stable flow condition in all the system. All the marine clay geotextile filter system reached stable flow condition, but at different time interval. The loss of clay particle during filtration process is more in marine clay and WJT 550 filter system compared to the other system. There exists good filtration compatibility between the marine clay, polymer or natural oven jute geotextile 775, oven jute geotextile 700 and non-oven jute geotextile 680 filter for the given hydraulic and soil condition. Whereas marine clay oven jute geotextile 550 filter system is not a better filtration system. From the apparent opening size or AOS and the filtration test, the empirical ratio of O95 by D85 less than equal to 4.5 and O50 by D50 less than equal to 100 are suggested as marine clay retention criteria for jute geotextile. So, next is some absorption or discharge capacity test on the natural prefabricated vertical drain. So, it is very important to understand that what should be the absorption capacity of the natural prefabricated vertical drain with time. So, we have the perform assigned model 2012. This is the 4 different types of natural prefabricated vertical drain, that is 1, 2, 3, 4 as well as the polyester prefabricated vertical drain. So, here graphs shows that absorption capacity in percentage versus the time in hour for both the natural prefabricated vertical drain 1, 2, 3, 4 and the polyester prefabricated vertical drain. So, in case of the polyester prefabricated vertical drain, you can see here that water absorption capacity is less and the time passes, then water absorption capacity remain constant with the time. Whereas, in case of natural prefabricated vertical drain, in case of 2 NPTT 2, you can see that absorption capacity is too high in terms of percentage and within a short time and then remain constant. And for other case 143, this is almost that constant water absorption capacity with time and then remain constant with passage of time. So, natural, we can say the natural prefabricated vertical drain has a good absorption capacity. Now, we have also performed rubber membrane confined discharge capacity test. So, this is the schematic diagram of the discharge capacity test apparatus. This is the longitudinal section and this is the transverse section, which we have also covered in the filtration and drainage chapter. And here the test apparatus with the loading plate. This is the loading plate and this is the top unit, this is the middle unit and this is the bottom unit. You have to place this geotextile material somewhere here or here, and the top and bottom is that any impermeable material, and then the water can flow pass through this geotextile material along the plane of the geotextile and then under the different application of the load. So, then you can calculate what will be the discharge capacity. So, these are the some result of rubber membrane confined discharge capacity test. Because water should not pass the top and the bottom, that is why it is provided with the impermeable material. And from this test, here variation of discharge capacity of the natural prefabricated vertical drain and the polyester prefabricated vertical drain at normal compressive stress at different hydraulic gradient. This is very important, that hydraulic gradient value, because sometimes you can see the hydraulic gradient value is given 5, 10, 15. If the hydraulic gradient is high, your discharge capacity also will be the high, but it should obey the Darcy's law. It should be in the laminar flow condition, not the terminal flow condition. So, here from this discharge capacity test, this relationship between the discharge capacity and the normal pressure. You can start with 50 normal pressure. At a particular time you are collecting the water, what will be the quantity of water at a particular time due to the applied load is 50, and then you calculate what will be the discharge capacity. Similarly, the next is 100 normal compressive stress, 100 kilopascal, then water is passing through the geotextile material and you are measuring what will be the discharge capacity at a particular time. Like that you are continuing 250 and even then more, and then you are shown the relationship between the discharge capacity and the normal compressive stress for a hydraulic gradient I is equal to the 1. So, you can see that discharge capacity is decreasing with increasing the pressure, and then it will be in a stable condition. But in case of the PBBT, polyester prefabricated drain, you can see that discharge capacity almost remain constant. So, all such cases have also performed under different hydraulic gradient. Here suppose hydraulic gradient is 0.5, here hydraulic gradient 0.25, here hydraulic gradient is 0.1. So, all cases you can observe that discharge capacity is decreasing with the increasing the normal compressive stress. Here also this curved discharge capacity variation of polyester prefabricated vertical drain and the natural prefabricated vertical drain under different hydraulic gradient. We are considering here is the different hydraulic gradient 0.25, 0.5, 0.7 or 1, and for a compressive stress. So, you can see here 10 kilopascal, 50, 100, 250 like that. So, you can see that what should be this value. So, you can see it is increasing, and like this you can have a curve like this for case of PPDT. So, all the curve you can have the relationship like this. So, what will be the discharge capacity for the different hydraulic gradient and under this different compressive stress value. Here also the result for the marine clay confined discharge capacity test. So, this is the variation in the discharge capacity of natural prefabricated drain and the polyester prefabricated drain confined in a marine clay with compressive stress at different hydraulic gradient. So, this is hydraulic gradient 1, this is for 0.5, this is 0.25 and this is 0.1. You can see that how the discharge capacity is decreasing with increasing the pressure. So, all the either it is a natural prefabricated vertical drain or the polyester prefabricated vertical drain, the nature of the curve is the same. Here also the discharge capacity comparison between the rubber membrane and the marine clay confined NPTT 1, 4 and polyester prefabricated vertical drain at different compressive stress for hydraulic gradient A for 1 and for hydraulic gradient I is 0.1. So, Here you can see that in case of the membrane prefabricated vertical drain, you are having the discharge capacity almost that constant with the different confining pressure. Here also almost similar nature of the curve. But in case of natural prefabricated vertical drain with the marine clay, you can see that discharge capacity is decreasing with increasing this confining pressure here also. For all other cases, it gives the similar in nature. Here the comparison of the present study result at a 0.5 hydraulic gradient between natural prefabricated vertical drain 1 and the 4 and prefabricated vertical drain made from the natural geotextile of other researcher. And you can see this is the natural prefabricated vertical drain 4 in this present study, and whatever the other study have been done, type A, Rao and Balam 1997, FD2, also JUG ETL 2001, and natural prefabricated vertical drain, that is also 1 in the present study, and FDB Kim ETL 2006, and natural prefabricated vertical drain 4 marine clay and in the present study, and NPTT 1 marine clay in the present study. So here also you can see that how the discharge capacity decreasing with increasing the confining pressure, and it has been compared with the all other authors. So we come to some summary and conclusion that natural prefabricated vertical drain 2 made from non-woven jute geotextile filter wrap around coir rope has the greatest water absorption capacity, and the polyester prefabricated vertical drain has the lowest absorption capacity. You have observed that from the curve, all the prefabricated vertical drain reached almost their maximum absorption after 2 hours of soaking in water. Beyond 2 hours, there is a negligible increase in the absorption capacity. The discharge capacity is greater in the prefabricated vertical drain than in the natural prefabricated drain. Also, the discharge capacity reduction rate is greater in the natural prefabricated vertical drain than in the polyester prefabricated drain, when the compressive stress is increased at a specific hydraulic gradient. So, you should maintain that hydraulic gradient. By confining the prefabricated drain in marine clay during discharge capacity test, the discharge capacity of prefabricated drain reduced by 40%, natural prefabricated vertical drain 3, 4 by 50%, and natural prefabricated vertical drain 1, 2 by 60% compared to rubber membrane confined discharge capacity test. So, some summary and conclusion from this result, that natural prefabricated vertical drain 4, which is made of woven jute filter and corrugated coir mat core, has a greater discharge capacity than the natural prefabricated vertical drain 1, 2 and 3 at the normal stresses and hydraulic gradient studied. The lowest discharge capacity is observed in natural prefabricated drain 2, which is made from non-woven jute filter wrapped around coir ropes. Flow condition through all the natural prefabricated vertical drain are linear at all the hydraulic gradient, satisfying the theoretical requirement for prefabricated vertical drain. So, we observed that the natural prefabricated vertical drain which satisfy this all the criteria, your discharge capacity, your clogging criteria, your permeability criteria, as well as the apparent opening size of the geotextile criteria. So, it satisfies all the criteria. So, one can make use of this kind of non-woven prefabricated vertical drain for the construction purpose. Now, I have also studied some large scale laboratory consolidation test. That what is happening if you use this material in a large scale consolidation test. So, this is the right side, this is the large scale consolidation test is in progress, and this is the schematic diagram developed and fabricated large scale consolidation test setup by Dr. Asha. What here is the natural prefabricated vertical drain, and here also the drainage system, this there is a drain, and also at the top of this is the marine clay, and the top of this is provided with a non-woven geotextile material, then the gravel layer, then the loading, and then by the dial gauge reading you are measuring, you are applying the load and you can measure. So, from this large scale consolidation test, so this is the stage of loading first set of test, and we will show later the graph measure settlement versus also the time curve here, without and with the different prefabricated vertical drain. So, this is, you can see that what is happening with the time stage loading in first set of test. It takes this time, you can see that with the time what is happening in the settlement. Okay. Then again that after the loading of this 50, and then with respect to the time, here you can see how it is with respect to the time this settlement is occurring. And then after some time it will be also stabilized, but you require maybe very large scale consolidation test which can give you the much more the equilibrium state of the soil, or it will be stabilized at a longer time, where here seems to be for the limitation of this equipment. So, you will be able to say that up to this days the settlement may be occur, that maximum what you can obtain from this curve. Now, here also the stage loading for the second set of test, and here is the curve, the graph settlement versus the time for the marine clay. So, this is the vertical stage in kilopascal, this is the time in days. So, this is the stage loading, you are giving the stage loading like that, like it takes time, then again load takes time, like this. You can see that after up to 150 kilopascal the vertical stage, and this days past is constant. After that 20 like that nearer, then it is constant. Similarly, that settlement curve with the time for various prefabricated drain, natural prefabricated drain, and also marine clay without this prefabricated drain. Without prefabricated drain, you can see this is the nature of the curve, whereas that with the prefabricated drain, you can see the settlement is more with the PVD, that means consolidation time within a short time it can give the better settlement. So, some numerical simulation of consolidation test using the software Flaxis 2D 2010 have performed. So, here the typical geometry for the numerical simulation of large scale consolidation test. This is the model of the marine clay without the prefabricated vertical drain, and this is the model for marine clay with PVD drain. You have provided PVD drain is here, and this size is about 240 millimeter, this is 650 millimeter, and there is a gravel about 50 millimeter, and then you are applying the vertical stress. And you will see, and this is the vertical drain here. Okay. So, we want to see that behavior of the prefabricated vertical drain when it come in contact with the marine clay. The another important point, that equivalent diameter of the band in shape, that is PVD, this is after Rixner 1986. If this is the width of the prefabricated drain, if this is the width is equal to the B and this thickness of the prefabricated drain is T, then equivalent diameter D will be equal to 2 into B plus T divided by pi, which is given by Ansbo 1979. So, here what I want to mean, that most of the cases that it has been observed that in general the sandane, the diameter of the sandane is about that 66 millimeter. For example, that if we find that width of the prefabricated vertical drain is 100 millimeter and this thickness of the prefabricated vertical drain is 5 millimeter. So, if you can substitute this value, that means that is 2 into 100 plus 5 divided by pi. So, 105 into 2, that means almost 210 divided by pi. So, this will give almost this value about 65. So, that the way that equivalent diameter of the sandane has been considered. So, I will maybe later on tell about more about this. So, from this soil property and the drain parameter used in this numerical simulation. So, this is the parameter used for the marine clay, and this is the gravel, that unsaturated unit weight in kilonewton per meter cube, for marine clay 14.5, gravel 17, saturated unit weight for marine clay 14.5, and this is the 18. That initial horizontal permeability of the soil meter per day 0.60 into 10 to the power minus 3, and here it is 1. Initial vertical permeability of soil meter per day 0.60 into 10 to the power minus 3, and for gravel 1. Modified compression index is 0.085, modified soiling index is 0.02, initial void ratio 2.75, effective cohesion is 1 kilopascal, and effective angle of internal friction 25 degree, in case of gravel 35 degree. So, these are the properties has been included in the computational analysis for simulation. Apart from this, you are to provide with the elastic modulus, that is for gravel 21000 kilopascal, permeability change index is 1.3, diameter of the cylinder influence of the drain is 480 millimeter, length of the drain is 650 millimeter, and type of the PVD. So, equivalent diameter, this I was trying to tell you, that equivalent diameter PVD for natural prefabricated vertical drain 1 is 61, natural prefabricated vertical drain 2 is 62, natural prefabricated vertical drain 3 is 64, natural prefabricated vertical drain 4 is 68, and polyester prefabricated vertical drain is 67. So, this is important, that how you can calculate the equivalent, that diameter that is d of E. So, as I said, for this sand we use about 65-66 millimeter, and that equivalent diameter has been determined using that earlier equation, and then you can obtain these are the value of equivalent diameter of the prefabricated vertical drain. So, after this input you can have this comparison of numerical and the experimental result obtained for the marine clay model with and without natural prefabricated vertical drain. So, here is the vertical stress versus this time, here the settlement versus this time. You can see that earlier also it has been shown like this, the vertical stress with the time, and here you can see the settlement for the different natural prefabricated vertical drain and polyester prefabricated vertical drain, and even then only the marine clay without prefabricated vertical drain. You can see that nature of the curve is like this. So, with this passes also it stabilizes. So, here the excess pore water pressure development and distribution showing the effect of drain in numerical simulation. Here is the pore water pressure with the time. So, this is the for marine clay alone model, and then marine clay alone model at mid depth of the location, and marine clay with NPTT4 model away from the drain at the mid depth of the location, and marine clay NPTT4 model near the drain at the mid depth of the location. You can see for the different location, even then if you take and you find that what will be the pore water pressure variation with respect to the time. So, you can see the pore water pressure is increasing with up to maybe 20 days, and then it abruptly decreasing with increasing the time. So, you can have the idea how the pore water pressure varying with the time. Also, some computational with the excess pore water pressure distribution pattern in the numerical simulation, A with the marine clay alone model, and B with the marine clay with the natural prefabricated vertical drain. So, you can see that here what will be the excess pore water pressure, this developed under the different that pressure. So, you can see here that what will be the excess pore water pressure here, and you can see that how the excess pore water pressure dissipated. So, what is the summary and the conclusion? That large scale consolidation test have shown that all the natural prefabricated drain and the polyester prefabricated drain aided in acceleration of the primary consolidation process in marine clay soil. The rate of settlement in all the marine clay installed natural prefabricated drain and the polyester prefabricated drain is almost same. The effect of different polyester prefabricated drain in terms of oil resistance and hence its effect on settlement rate could not be compared distinctly. Clogging of the core of the natural prefabricated drain and the polyester prefabricated drain are not observed after the 65 days period of consolidation test, which we can only perform. Now, main summary and conclusion from the above test, that numerical simulation of experimental consolidation behavior of marine clay with and without natural prefabricated drain and the polyester prefabricated drain can be made reasonably well through drain element option and permeability change index soil parameter. The developed and fabricated natural prefabricated drain are eco-friendly, easy to fabricate and low cost material which can be used to accelerate the primary consolidation process in marine clay. Now, what are the major contribution from this test? The development and fabrication of 4 type of the band shape prefabricated drain made from single layer woven and non-woven jute geotextile as filter and coir ropes or coir mat as core designated as natural prefabricated drain or NPDD1, NPPT2, 3 and 4. NPVD4 made from the woven jute filter and corrugated coir mat core has a high discharge capacity and better drainage characteristic. I say that discharge capacity also very important. Application of long term filtration and hydraulic conductivity ratio test on marine clay jute geotextile system. The filtration tests are a viable method to evaluate compatibility of the jute filter with soil. All the natural prefabricated drain aid in acceleration of the primary consolidation of the marine clay. Apart from this, the natural prefabricated drain are more appropriate, low cost, alternative choice to polyester prefabricated drain, especially in developing country like India, because of the following salient factor: that the natural prefabricated vertical drain is technically feasible, it is more economical, low energy utilization, and it is a sustainable material, and also it is eco-friendly and environmental friendly. So, we can make use of the natural prefabricated vertical drain because it satisfies the all the criteria like the polyester prefabricated vertical drain. Now, how to this design and what are the equation we can adopt to design the prefabricated vertical drain. Improvement in the consolidation behavior of soil due to the natural prefabricated drain can be predicted numerically based on the theory of radial consolidation originally derived by the Barron 1948 with subsequent modification by Hansbo 1979 and 1981. The equivalent vertical permeability KVE was derived based on the one-dimensional vertical consolidation theory and Hansbo's 1981 unit cell radial theory. So, here KVE is the vertical permeability of the soil is equal to 1 plus 2.6 into H square divided by nu into d square to kh by kb into kv, or mu is equal to n square divided by n square minus 1 into ln n minus 3 by 4 plus 1 by n square minus 1 by 4 n to the power 4, where kb is the vertical permeability of the soil, kh is the horizontal permeability of the soil, and d is the diameter of the cylinder of influence of the drain, and mu is the shape factor with smear and oil resistance effect, and n is equal to d by d, where this small d is the equivalent diameter of the band shape drain. So, here capital D is the diameter of the cylinder of influence of the drain and small d equivalent diameter of the band shape drain. So, here what I was trying to say that equivalent diameter of the drain. the band shape that prefabricated drain can be converted into equivalent circular drain based on the Hansford 1981 expression. So, this equivalent diameter dW will be 2 into A plus B by pi, where this is the A, that means width of the drain, and this is the B, is the thickness of the drain. So, dW will be equal to, this is the equivalent circular drain. So, dW will be equal to 2 into A plus B by pi. So, this is the band shape prefabricated drain. So, this is important, that how you can calculate the equivalent diameter of the PVD. So, if you know that what is the width of the PVD, if you know what should be the thickness of the PVD, so then you can calculate that what should be the equivalent diameter of the PVD. So, adopting the equivalent vertical permeability concept, Asa and Mondal 2011 numerically simulated the laboratory model with finite element analysis. This is the comparison of the settlement obtained from the experiment and the finite element analysis. So, you can see here the time versus the settlement for various prefabricated vertical drain. So, you can see that how the settlement is increasing with the time, then after a certain time again the settlement is increasing like this for all this PVD. You can see, you can match between that what will be you have obtained from the experiment and also the finite element method. So, it has been observed that it is quite good matching between the experimental and finite element method, and the predicted settlement from finite element method is closely matched to the laboratory consolidation test. So, you can have that we have performed the different type of the test, and also we have performed that numerical analysis using the flaxes as a finite element method, and it has been observed that it is matching well. So, natural prefabricated vertical drain can be used for the ground improvement. With this, I finish my lecture today. Let us hear from you any question. Thanks for listening.